So this is the third video in our review of linear equations and linear algebra. And in this video we're going to be looking at worded problems essentially, so constructing equations or constructing formulas or constructing expressions that represent situations. It's really important that you understand that in maths, when we're asking you to solve a worded problem through year 9 and 10, we're not interested in the answer to the problem so much as what we're really keen that you're able to learn how to do is translate the worded information into algebraic information. That's the skill that you need to build. And if over the last 2 years you've spent this time just sort of focused on the answer to the problem and just trial and erroring until you get the answer, you've missed the opportunity to build your ability to translate between those two languages, English and algebra. Okay? And without that flexibility, you're going to have real difficulty in this subject. There's a lot of problems and being able to decipher and interpret and understand and create equations in maths methods. It's a highly analytical subject. Just being able to solve the equations is not going to get you very far. Okay, so some tips, because I often find that students, they read a worded problem and they go, I can't do it, I don't know where to start. Okay, you have to start somewhere. The key thing is to move away from that idea that you should be able to look at the question and know exactly what you need, what the next 5 steps you need to do to solve the problem are. You don't need to know the sequence of 5 steps. You just need to come up with the first step and do it. And then from that, come up with the second step and do it. So, as I said, the first step is that you can't always expect to be able to just write down the equation. Okay, you might need to build up various terms. You might need to think about, okay, well, how can I express the profit and how can I express the costs, and then how can I put that information together to make an equation, or how can I express the time that train A took, and then how can I express the time that train B took, and then how can I combine those expressions together to form an equation. Okay, so step by step, build it up gradually. Don't be afraid to write some words. Okay, you know, train A time equals train B time equals. Oh, right, then the question tells me that train A time plus 20 minutes equals train B time. There's my equation, okay? Don't be afraid to write words, to be clear about what your expressions are representing, to define your variables carefully. X equals what? X doesn't equal apples. Does X equal the number of apples, the cost of the apples, the weight of the apples? Okay, be really precise. What units is it in? So that you can then be clear about when you put that information together in an equation. You need to be confident with the meanings of mathematical words, such as sum, product, difference, remainder, total. What do those things mean? So sum is the sum of two things is when you add them. The product of two things is when you multiply them. The difference of two things is when you subtract them. The quotient of two things is what you get when you divide them. Okay, these words need to be familiar things to you. You must take care with units. Are you equating expressions that are in the same units? And that's why I think it's important when you define your variable, define what units it's in. Have you inadvertently made that expression in cents and that expression in dollars, and therefore it doesn't make sense to equate them? Or is one in kilometres and one in metres, therefore you can't actually equate them, so you need to think about your units. Sometimes it's really helpful to organise your information. Okay, again, you can't get straight to the equation, but thinking about, oh, actually there's a lot of quantities in this problem. You know, particularly I'm thinking of problems that involve distance, speed and time. And you might have train A and train B, or, you know, running and swimming, or whatever it might be. You might have two different people doing 3 different things. And therefore then you've got 6 variables, plus maybe some totals. Organise that information first, then look at how you can put it into equation. I'm a strong advocate of a table, particularly for problems involving distance, speed and time. And the other one I use a table in is the classic, you know, John is 3 times as old as his brother, and in 10 years' time he'll be half as old as his brother. That doesn't make sense, but whatever it is. Again, there's 4 quantities there. There's 2 people, and there's 2 different time periods. Organise that information first, then work out how you can build an equation from it. And your equation is a mathematical sentence. Read and translate it carefully, and to ensure that it accurately represents the information in the question. Try and write out a worded equation, you know. Cost of apples minus cost of pears equals $3.20. Then put your expression for the cost of the pears in and the expression for the cost of the apples, okay, whatever it might be. Okay, sometimes the simplest sentences can be the hardest to form into an equation. I want you to take real care with these in example 1. I want you to pause the video, have a go at writing down the answers yourself first, and then let's have a chat about them. Okay, so we want to write a formula or construct a formula using the given symbols. We want to write a formula that connects the number of days, which is D, in W weeks. So if we have W weeks, how many days is it? Now what a lot of you will do is say there's 7 days in a week. That's the sentence you'll construct, but that's not what's happening, okay? We have W weeks. In 1 week, we have 7 days. Okay, in 2 weeks, there's 14 days. In 3 weeks, there's 21 days. In W weeks, there's not 7 days. So if we want to connect if we have W weeks, the number of days is equal to 7 times the number of weeks. Okay, the number of days, which is D, is equal to D, we're multiplying by 7. D is equal to 7W. The number of days is equal to 7 times the number of weeks. And actually that's where it's important that your variables are clearly defined. D doesn't equal days. D is number of days. And W equals number of weeks. Okay, so therefore when you say there are 7 days in a week, you're not interpreting the variable correctly, because actually, read the sentence properly, it says 7 times the number of days equals the number of weeks, which is not true. If you write down an equation, check it, try it. Okay, let W equal 2. I know it should give me 14, tell me that D equals 14. 7D equals 2, oh, hang on. It doesn't tell me that D equals 14. Something's not right. Okay, as I said, these are the places you'll make mistakes. Similar, the number of cents in D dollars. Okay, so again, be clear about C is the number of cents. D is the number of dollars. Okay, so therefore, when you say to me, there is 100 cents in a dollar, therefore that's the equation, it's not correct, because your sentence is saying 100 times the number of cents will give me the number of dollars, whereas actually it's the opposite of that. The number of dollars is equal to, the number of cents is equal to 100 times the number of dollars. i.e., if there are $3, that equals 300 cents. Sub a number in, check that you've got it right. Be clear about what your variables are so that you can accurately convert them into an algebraic sentence. Okay, when solving a worded problem, consider the following steps. Okay, number 1 is clearly define your variable. So as I said, be clear about the fact that D represents the number of days, not just days. Okay, because then your equation should read as a fully formed and accurate sentence. The second thing is to come up with expressions for the necessary quantities. Okay, just focus on all the separate bits of the problem first, and then think about how you can put them together into an equation in step 3. Note that the number of equations must match the number of variables. So if you introduced 2 variables at the beginning, you're going to need 2 equations in order to solve it. I'll quite often find that questions which the textbooks list as being simultaneous equations examples, I can quite often go straight to setting up 1 equation. And that's about actually taking some time here at step 2 by coming up with expressions for the different quantities and then building the equation. Solve the equation or equations you've ended up with. And then number 5, which is really important, answer the question. Again, this is something I'll say commonly through year 12 and as we're doing exam revision and all those sorts of things. Answer the question. What does it ask for? It doesn't ask you to find X, you've introduced X yourself. It asks you to tell you how old John was. Therefore, John is 42 years old. Okay? Or it asked you for the number of apples. Therefore, 17 apples. Okay? So, not A equals 17. Alright, or you may have ended up, your equation may have given you the number of apples, but the question's actually asking you for the number of oranges. Or the question might ask you for both the number of apples and the number of oranges. Make sure that you've answered the question. Okay, solve each of the following problems by setting up and solving an equation or equations, I should say. Okay, example 2. So 3 consecutive integers add to 72. Find the largest of the 3 integers. Okay, so we need to understand what this word consecutive means. It means 3 and integers. Integers are whole numbers, positive or negative. Consecutive means that they're 3 numbers in order. So 3, 4, 5 is 3 consecutive integers. 3, 7, 11 is not 3 consecutive integers. Yes, there's a pattern, but they are not consecutive integers, one after another. Okay, so we need to introduce a variable. We want to find the largest of the 3 integers. So maybe we let x equal the largest integer. I'd probably let x be something different, but let's start with this. Okay, so then what we want to think about is, okay, well, what's the second largest integer? Or what's the middle integer? And how can we express the smallest integer? Okay, remember they have to be consecutive, which means plus 1 plus 1. So that therefore means minus 1 minus 1. So the middle integer will be the largest integer, take away 1. And then the smallest integer will be the largest integer, take away 2. Personally, I probably would have set it up as letting the middle integer be the unknown, and then your biggest one is x plus 1 and your smallest one is x minus 1. But you'll get there. It makes for a slightly neater equation, but you'll get there in the long run. So therefore, our equation we can now form is we know that the sum of the integers is 72. They add to 72. So therefore, the largest integer plus the middle integer plus the smallest integer equals 72. Again, the sentence should read accurately. Largest integer plus the middle integer plus the smallest integer is equal to 72. It's exactly what the question says. Now solve your equation. So 3x minus 3, collecting like terms on the left, equals 72. So 3x equals 75, adding 3 to both sides, and dividing both sides by 3, 75 divided by 3 is 25. So therefore, the largest integer is 25, which means that the 3 integers, if the question had said find the 3 integers, that would be 23, 24, and 25. It might say find the smallest integer, whatever it is. Make sure that you've answered the question. Alright, example 3. 65 lollies are divided amongst 3 friends so that Alan has twice as many as Brendan and Chris has, sorry, it should be a column there, has twice as many as Brendan and Chris has 1 more than Brendan. How many lollies does Chris receive? Okay, so the question asks us how many lollies Chris receives. So we could let our unknown be Chris, as the number of lollies Chris has. But looking at the information, the 2 bits of information I have is Alan has twice as many lollies as Brendan and Chris has 1 more lolly than Brendan. So we're told about Alan and Chris's lollies, both of them compared to Brendan's lollies. So it's going to be much easier if we let the unknown be Brendan's lollies. Okay, so let B equal number of lollies Brendan has. Okay, which means that Alan has twice as many as Brendan. So 2b is the number of lollies Alan has. And Chris has 1 more than Brendan. So Brendan plus 1 is the number of lollies that Chris has. So again, we haven't focused on being able to write down an equation straight away. We're introducing a variable first of all. We're expressing the other quantities in the problem in terms of that variable, and then we can build an equation. So the information that will allow us to build the equation is that there are 65 lollies in total. So the three quantities add up to 65. Brendan's lollies plus Alan's lollies plus Chris's lollies all equal 65. B plus 2b plus b plus 1 equals 65. So collecting like terms on the left, that's 4b plus 1 equals 65. 4b equals 64. And so b is 16. Now, the question asks for how many lollies Chris has. Now, Chris has b plus 1 lollies, so that's 17 lollies. So therefore, Chris has 17 lollies. Okay, so it's important to answer the question. B equals 16 is not your answer. Make sure that you're clear about which quantity the question wants you to give for the answer. Okay, example 4. Jackson has a square garden bed in his yard. He decides to enlarge the garden bed to make it 1 metre wider and 2 metres longer than it is currently. If the area of the new garden bed will be 14 square metres larger than the original garden bed, find the dimensions of this new garden bed. So what I find students do is they read this, there's a lot of information, 2 sentences, it's all confusing, and they put their hands up in the air and go, I don't know how to do it. Okay? Read it through once, go back, and then break it down. Jackson has a square garden bed in his yard. Okay, so he's got a square. Let's say that it's x by x. He decides to enlarge it to make it 1 metre wider. So he's going to add 1 on there. And 2 metres longer. He's going to add 2 on there. Okay, so that's the enlarged garden bed. If the area of the new garden bed, so that is the bigger one, will be 14 square metres larger than the original garden bed, find the dimensions of the new garden bed. Okay, so new area equals original area plus 14. So 14 square metres larger, add 14 metres onto the 14 square metres onto the original area, and you've got the new area. Can I just be clear about, don't put units in equations, okay? You know, it's very confusing. Is that m squared? Is that algebra? What's happening there? Make sure, obviously, that everything is in the same units, but don't write the units in the equation. Just put the units on the final answer when you get to that point. Okay, so let's think about these things. The new area, so the new garden bed is this red one. And it has dimensions, that's x plus 2, and that's x plus 1. So the new area is x plus 1 times x plus 2. The original area was just x times x, that's x squared. So there's our equation. Now we focus on solving it. Let's expand out the left-hand side. Expanding brackets should be pretty efficient by now. X squared plus 2x plus 1x, so plus 3x. Try it, we should be past the point of needing to write out plus 2x plus 1x, okay? Try and do that middle step in your head. Plus 2x plus 1x, that's plus 3x, and then plus 1 times 2, which is 2. Again, these are bread and butter skills that we haven't got time to be spending 3 lines expanding brackets. We need to be able to do it quickly because what we're trying to do is much bigger than that. It's just simply one step in a larger problem. Okay, we can take away x squared from both sides, so it looks like it might be a quadratic equation, but it's actually not. Take away 2 from both sides, and divide both sides by 3, so x equals 4. Now let's go back and see what the question actually asked us for. Find the dimensions of the new garden bed. Okay, so the original garden bed was 4 by 4. The new garden, is x plus 1, so that's 4 plus 1, so it's 5 metres by x plus 2, 6 metres. Again, you should be able to check. The original one was 4 by 4, so that's 16 square metres, and the new garden bed is 5 by 6, which is 30 square metres, so that is 14 square metres bigger. Okay. Alright, example 5. I am 1 more than 11 times as old as my son will. In 9 years, I will be 7 more than 3 times as old as him. How old is my son? Okay, so this is one of those classic examples I referred to earlier. Here we have 4 different quantities. We've got me, Will, who's my son, and our ages now and our ages in 9 years. Okay, so I'm going to set up a table to organise that information. So I'm going to have me, Will, and I'm going to have now and in 9 years. Okay, let's focus on the now column and this first sentence. I am 1 more than 11 times as old as my son Will. Okay, so my age is described in terms of Will's age, so I'm going to therefore let Will's age be the unknown, regardless of what the question asks for. It does say how old is my son, so that's the quantity I want to work out, but I wouldn't let that drive what I let x be. Okay, let let x be the thing that's going to make it easier to set up the equation. Okay, so if Will is currently x years old, I am 1 more than 11 times as old as Will. So 11 times Will's age plus 1. Sorry, got to be legible there. Let's go again. 11x plus 1 is my age. Okay, now I advocate at this point, forget the second sentence. The second sentence is what we're going to use to make the equation. We should be able to fill in the table. Once we've filled in one column of the table, we should be able to fill in the other column. Because to get from now to in 9 years is adding on 9 years. So therefore, if Will is currently x years old, in 9 years' time, he'll be x plus 9 years old. If I'm currently 11x plus 1, I'll be 11x plus 1 plus 9. So that is 11x plus 10. Okay, so now we've got expressions for our ages in 9 years. We can use the sentence about what's happening in 9 years' time. Okay, in 9 years, so using the variables in the green column, I will be 7 more than 3 times as old as him. So again, sometimes it helps to write out the sentence in words. Okay, so my age in 9 years is equal to 7 more than 3 times as old. So 3 times Will's age in 9 years plus 7. Okay, again, interpret it. My age in 9 years' time is equal to 3 times Will's age in 9 years' time plus 7. Okay, the error that students make here is they do Will's age now and they put x there. Okay, but then the second sentence doesn't make any sense. The second sentence doesn't say in 9 years time I will be this calculation as much as his current age. It's in 9 years time. This is the connection between our ages. So you need to use the in 9 years time age for both of you. Oh, sorry. Just gonna get rid of that. Okay, so my age in 9 years time is 11x plus 10 plus 3 times Will's age in 9 years time, which is x plus 9 plus 7. Okay. Alright, so 11x plus 10 equals 3x plus 27 plus 7. So we've got the equation, now we're just focused on solving that, then we'll worry about answering the question. So 11x plus 10 equals 3x plus 34. Let's take away 3x from both sides, that gives us 8x, and take away 10 from both sides, equals 24. So x equals 24 divided by 8, which is 3. Now, what does it ask for? It could be asking for any of those 4 quantities or more than one of them. It could be asking for my age now, Will's age now, my age in 9 years' time, Will's age in 9 years' time, or any combination of those. The question says, how old is my son? The implication of how old is my son is how old are they now? And so that's what we found, that's x. So therefore, the son is 3 years old. And again, you should be able to check it. So if the son is currently 3 years old, so let's fill in over here. If the son is currently 3 years old, that makes me 11 times 3 plus 1, so it's 33 plus 1, so 34. In 9 years' time, that would make me 43. And Will will be, in 9 years' time, Will will be 12. And the relationship at that time is I'll be 7 more than 3 times as old as him. So 3 times 12 is 36, plus 7 is indeed 43. So it all works. Okay, last example. Example 6 is a classic distance, speed, time. Nathan is training for an Ironman competition. On Saturday, he trained for 6.25 hours, completing a bike ride followed by a run. He cycled at an average speed of 30 kilometres per hour and ran at an average speed of 16 kilometres per hour. If he travelled a total of 170 kilometres, find the time that he spent on the bike. Okay, there are lots and lots of quantities here. There is distance, speed and time for the run and for the cycle, and then there's also information about totals. Okay, so let's be clear what's happening. Let's set up a table. I'm going to have distance, and I'm going to have time, and I'm going to have speed. And I need to be consistent about units here. Use the speed to guide the units. So if the speed is in kilometres per hour, the time needs to be in hours, and the distance needs to be in kilometres. Okay. Alright, then we're going to have, what does he do? He does a bike ride and then a run. Okay, so let's have the bike and the run. And then we might also have information about totals, which we do because we've got the total distance. Okay, total speed's a meaningless concept. Can't have total speeds, there shouldn't be anything in that box, but there are 8 quantities that we're dealing with here. Let's fill in what we know. He trained for 6.25 hours, so that's the total time. So 6.25, that's 6 1/4, which is going to be 25 on 4 hours. You can leave it at 6.25, but at some point in the equation solving, you're probably going to need to make it a fraction. He cycled at an average speed of 30 kilometres per hour, so the cycling speed is 30 kilometres per hour, and he ran at an average speed of 16 kilometres per hour, so that's the running speed. If he travelled a total distance of 170 kilometres, so total distance is 170, find the time that he spent on the bike. Okay, so no reason not to let that be the unknown quantity, so we want the time spent on the bike. Alright, so then we should be able to fill in everything else using the totals and also using the connection between distance, speed and time. Okay, so we know that speed is equal to distance over time, and we know that from the units, kilometres per hour, distance units divided by time units. Okay, and then every other quantity we can get to by rearranging that. So if we look at the bike column, for example here, it's only the distance quantity we're missing. So distance, distance, if we rearrange this, is speed times time. Some of you might also be familiar with the triangle, speed, distance, time, okay, where you cover up the thing you're looking for. So if you're looking for speed, you cover up speed, and then speed is distance divided by time. If you're looking for distance, then you cover up distance, and distance is speed multiplied by time. And similarly, if you're looking for time, cover up time, and time is distance divided by speed. Okay, so we are looking at distance is speed times time, so that's going to let me fill in that box there. Okay, so distance is speed times time, so that means the speed of 30 times the time of t, the cycling distance is 30t. Alright, we should be able to fill in this quantity here by using the total time. Okay, if there's a total of 6.25 hours and t hours of that was on the bike, then 6.25 minus t hours was spent running, or 25 on 4 minus t. Okay, and again, the running distance is going to be the running speed times the running time. So it's going to be 16 times 25 on 4 minus t, or 16, or 6.25, if you're more comfortable with that. Alright, then where are we going to get our equation? Okay, well our equation is going to come from this row here, because we haven't used that 170 kilometres yet to build anything up. So the total distance, so the cycling distance plus the running distance is going to be 170. So we have 30t plus 16 times 25 on 4 minus t equals 170. So we've formed our equation. And this is what I mean by you cannot expect to just write down that equation. Look at all the work we had to do to come up with all the different variables and work out how to build the equation. You've got to be able to take it a step at a time, and you've got to be prepared to invest the time. Okay, so now we can solve our equation. We want to expand out this bracket. Okay, when we do 16 times 25 and 4, let's not do 16 times 25. Let's recognize that the 16 and the 4 will cancel down, and so it's going to be 4 times 25. Let's collect the like terms, so 30t minus 16t is 14t, and we've got 4 times 25 left there, which is just 100, equals 170. Subtracting 100 from both sides, so 14t equals 70, dividing by 14. 7's a common factor there, it's 10 on 2, and so that is 5. Alright, so we wanted, t was what we're trying to work out, the time that he spent on the bike. Therefore, Nathan cycled for 5, what were the time units? Hours. 5 hours. He's an Iron Man. So he cycled for 5 hours at an average speed of 30 kilometres per hour. Okay, I would strongly suggest that this worded problems is probably an area of weakness for most of you. And so the more practice you can get here, the better. Please don't shy away from really practicing. Try and bring in some of these techniques. Think about, could I use a table? Define your variable really carefully, and use those steps to help you build the equation rather than just expecting to be able to write the equation down straight away. So the combination of practice here from exercise 1B, 1D and 1F. I think 1B is probably the linear equations exercise, 1D is the simultaneous equations. I don't make a distinction between those two. Lots of people would have set up simultaneous equations here for this. I prefer to use the table and then try and build everything in terms of the one variable, and so I tend to go straight to an equation. So I'm not making a distinction between whether you set up one equation or two equations, just solve the problem. And then I think 1F is probably the formulas exercise. So there'll be a few examples, perhaps more like these first ones we talked about here, up here in exercise 1F. Okay, best of luck.